transponders, and transponders start communicating, and they start bringing in, they start talking with each other. But the first type of calibration is called relative calibration, where, as I said, you have components here. We have different components here. Like you hire a vessel, you're going to allot 10 transponders, and you have something called transceiver that should be placed on an ROV, and the communication between the ROV to the vessel can be done by two types. One is deploying the transceiver on the side of the vessel, or it can be taken through a fiber optic tether to the surface. From there, it goes to the LBL software. From there, it goes to the navigation software. So the relative aspect is measured, is as the name indicates, relatively where I am. So when the transponder comes to know where exactly it is, it's not really worry about this USBL position. It can be somewhere there. It can be anywhere. But it will only worry after it start talking with each other. So it's, the communication starts like this. So when the ROV sends a command to the transponder saying, hey, find out where you are. So then immediately the transponder gives this communication to rest of them, and rest of them will say, hey, I think you're here, I think you're here. So it all becomes, jumbles up and calculates, and that methodology is least square adjustment, which we shall not be talking too much today, but you shall only understand the method. So that everything gets adjusted and finally determines the exact position where it is. But still, you have to wait for some time, because through adjustments, the final position is derived. So the ROV sends the information of this to each and every transponder. So it individually brings each transponder to say where you are and find out where you are, adjust yourself, and just give the final results. So this is how it's happening. So once it's done and everything is done, so finally the residuals between the difference between where the original position, where the adjusted, you will come to know it looks like a big surprise, because each transponders are very powerful. They calculate internally, and it's a mathematical calculations where they take so many factors like communication, they take for the range, they take for the the height differences. That we shall see in the later stage how this mathematical calculations is happening. Sorry. So this is how exactly, as a relative starts the communication of the ROV sent to the transponder. Transponder calculates its position with respect to the others. It becomes a standard relative calibration. So what's the next step? As I said, the calibration is two types. So this is about the transponder, but as per the real, because since being in industry, I have deployed nearly 2022 LBL jobs in my life. So I have personally seen that, or not always the problem happens only with the transponders. There will be problems happen due to the offsets, and how to exactly understand, because the most important thing we shall be seeing today, every time we'll be discussing, is one sensor called sound velocity sensor. So people definitely take those things for granted. This is a thing that we have to carry out as much as sound velocity and update them, because at the end of the day, we are trying to achieve a kind of an accuracy where we should not make even a small mistake. We should not even really forget the things which is not to be considered. We have to consider everything. So in this absolute calibration, what exactly we does is, since we have carried out an array, we know the whole array plan, and we know what's the final point is, we should take the longest array. The longest array here. What is the reason being? There are two things you have to carry out an observed calibration. First thing is, observed calibration is happened like a boxing. Boxing means you spin around. It's a traditional USBL calibration method. You spin around a beacon and carry out with 40 to 100% of their depth. You just have to make a diameter and spin around. What exactly we are going to understand from that is the error in the multipath. That is, if there is any rebounding happens on the beacon, because the beacon is fixed and you are rotating, and second important thing is the sound velocity range error. There is a big chance that if we have a sound velocity issue, when you get the values and start doing your range computation, that's where you will understand that there will be sometimes it will be look high and there will be sometimes it look low, because you will get confused. because the velocity, sound velocity machine is right. That's something you have to be taken care of in the absolute. So it's a typical methodology of doing a boxing across this array with 40 to 100% of the depth. What is the depth? You make a diameter and just spin around that with a standard speed, and so that you will understand, along with this, you will also understand the range measurement error, what you do for the calculation because of the sound velocity. So as it is mentioned, is a surface vessel with a transceiver calibrates transponder at the long baseline to position with respect to the global coordinates. So when the rate calibration talks everything with each other, there might be instance that there may be something can go wrong, and can also the geodesy, the digital terrain model, which we should consider as a part of the scope. First thing we have to consider is the geodesy, that is how the digital terrain model is and what is the geodesy parameters and how we exactly. That's definitely, I'm very sure surveyors will take care of that one properly and also carry out all calibrations. Once that is all done perfectly, and we don't have a problem other than certain sensors here over this place. So when you rotate around and we carry out the array rotation and all those things are considered, so that finally we are absolutely sure that this array is perfect to carry out the operation. So what else? We just have to jump. Yes, you understand. So initially when I say the deployment time, which is proportional to the calibration time, exactly. So there's no doubt about it. And being the challenges in the last 2 years we have faced across utilizing by International Maritime Organization says to reduce the carbon emission to support a climate change. So the conventional LBL is definitely making a kind of impact on the carbon emission, at least to a certain restorative effect. So what is exactly next thing we will do? We're doing is the pushing. Once we have done with that, once we are happy, I am just doing this in a very short span of time, but believe me, there's a lot of things we have to consider to get this. It's going to take some time. If the more number of transponders is very good, but the more number of transponders is also increase your time and your efficiency. It increases efficiency, but the cost someday is not enough for your budgets. So then what's going to happen is the vehicle is ready to start the mission, and the vehicle is going to step on and carry out operation in between the array like metrology or out of flow line calculation or any kind of the subsea operation. It's very much there and is very confident because it has got number of transponders. It can able to support it. But the advantage is you have a very good redundancy of an acoustic. Acoustics is there and is very, very high redundancy. So, but the thing is, what for we are here for? We have just come here as I know that once we are working in the last 2 years, we just fed up on understanding the different methodologies, but we just thought to really start working on technologies which related to remote and autonomy. Because as you know, it is indirectly supporting the COVID, wherein the market is heading towards purely autonomy, residential, and long-term thing. So we thought that this kind of LBL operations is not something which can be utilized in taking the market towards forward. So that is where we identified the key 4 points which is bringing an impact. The first one is utilizing. I'm just not subjectively saying that an LBL operation, a surface vessel can emit more emission, but definitely is going to create an impact. It is going to be for a long time and it's going to take its own sweet time to carry out teaching. That's what the first thing. And the second thing is, since the advancement of technology is happening, that is more than long-term operations, like you are just deploying the system for months and months, years and years. This definitely something needs to be done. Wherein we can't deploy 10 transponders in the seabed for a year operation. It's not possible. So definitely we should find a method to ease the subsea operation. And third thing is time and consuming. That's what we have already discussed. And finally, we are looking for a methodology not as bigger as this, something which can be equal to this, but we can improve the efficiency and also maintain the accuracy. So that is where it starts with Sparse. So Sparse definitely, we are not going to come here. We are not being here to come and introduce a new method because Sparse is no newer. Sparse is very much old tradition. And actually, the thing is, being in Figaro, I've seen lot of some jobs they have really tried way along in 2010, 2011. They have tried replacing Sparse LBL in some of the construction jobs. But the advantages why today Sparse has come is we have to really thank the acoustics OEM who have really come up with lot of research. They have really invested their research time and bringing up a very fantastic advanced signal processing protocols, which really helps. And also, second thing, what they have done is they have improved the ranges. That is, they are not like they have not limited the ranges. Now, the transponders are talking is really 2 kilometers. I'm just saying it might be more also, but I'm just saying yes, 2 kilometers can talk with each other. And the transponders have become very intelligent. They are becoming very intelligent. You can add up more sensors and improve the capabilities. And like this, we just have a lot of advantages with that. And that really one of the biggest advantage of the Sparse LBL. But not only that, that's the most important thing is the inertial navigation system. So the moment when the inertial navigation system is being introduced to the Sparse LBL, it's not trying to come and eradicate the excessive amount of transponders. What exactly it does is it's just trying to come and help to make the deployment quicker and be able to plan and support the similar kind of a conventional LBL with the fewer transponders. That's it. But believe me, yes, most of you know, Inertial has got its own problems. Inertial has got problems like drift, and it has got its own errors like bias, and it has got its own thing called walkthroughs. It has got its settling time is not going to be easier, and it needs a lot of sensors to get added upon. So INS introducing into the LBL, it's just becoming a sparse. It's just trying to replace the excessive extra amount of transponders. But again, it also needs some references. It cannot be doing alone. It needs to be there. So that is what we have an illustration here. So Sparse LBL starts with most of the vehicles nowadays comes with an INS. So INS comes definitely, you know, all the reference, all the aiding sensors have to be done. You should have a DBL, you should have a depth sensor, you should have an altimeter, and you should have the SBL, and you just have everything added up together and just gives that information to Kalman filter to build a very good INS model. So that is a part of a package for every multi-beam. That's a part of a package for a pipe tracking, any kind of operations you do in the seabed. But here is bringing a very big role. What exactly is going to take is going to take ranges as well. So the first important point of a Sparse LBL method is to first fix your INS, because you are trying to say INS is more powerful and I want my INS to be one of the reference. So first thing is understand the scope and just draw wherever you want to measure, like from what point. For suppose this is one of the vehicle part where I have want them to work, and they say from a northwest to a southeast line. So then the next thing you should come to understand is how the error eclipse is going to be. The error eclipse of the inertial. Definitely inertial is not going to get settled down. It needs things. So prior to deploying the transponders, not like conventional, you should plan it perfectly. Like first thing is identify where you want to put the transponder. Then make sure you just have a solid angle of cut. So which all these terminologies are derived only from OEMs. So when we had a training, this is what the OEM taught us, that these are the things to be considered very seriously during the planning. But again, methods will change with each other. So once you have the angle of cut, but there will be a question that what is the angle of cut you are looking for? 60 to 120. So before deploying the transponders, you should know that what is the angle of cut is going to be. You're trying to get the position, you're trying to get the ranges onto the INS and compute a perfect INS model which can be used for tracking and for expanding, for extending. So many things it can be useful. But in the last slides, when we see, you just got 5 or 6 or many. But as for the many things they say, you just need to have a perfect tree with a very good reference can be a very good array to start with your work. So these advantages of this array is very longer because the transponders are longer in range. You can deploy them in a kind of a big area, and you just need to make sure that the angle is perfect so that the INS gets reference perfectly, so that from there it can able to always take the ranges into the consideration for any kind of tracking. So this is before the planning. So like the advantages you got here, I'm just trying to put it straight away that with reference to the conventional LBL, like you just have to deploy 3 transponders in the Subsea, and you know the time is less, and you're just going to save a lot of time, cost, as well as the advantages you're going to make it initial. But again, we are not left out with acoustics still now. So we have something called the calibration. So it is a standard television calibration. Like suppose we just say, is it what the advantages of Sparse LBL? No, it has got more better than that. It has got a calibration called 2D and 3D calibration. So the methods is differ with survey because it has got its own advantages and everything. But it has relatively the use of the relative and absolute, but it has got 2D, which the calibration done for the position, and whereas in 3D it will just take the position, depth, and the tide. So all these things are considered. But here we are just going to say something called extending the transponder. Suppose the advantage here is you can carry out everything with the help of a calculation called SLAM. What is SLAM? SLAM is basically simultaneous localization and mapping. That is, you have a powerful INS with you, and you are taking 2 solid references. Here in this case, we have 1 and 2 solid references. And what we are going to say is, with the 2, I am going to find the unconstrained transponder here, which has moved out. So what I am going to do is, I am going to take these 2 references along with an INS and a solid DVL. I'm just going to compress everything together, do the initial calculations, and tell them that, okay, I am very, very stronger now. From here, I know where you are. So this is what called the SLAM. SLAM is basically mapping the environment. So what exactly it does is just trying to map the boundaries of the map area and just get localized. So here, since it has got an INS and take the references with each other, it's very possible and it's very easy to calculate the unexpected or unconstrained position. So now you can see here how it does. So you just get the measurement from there, and it moves out. It just forms a straight line and just moves out. Again, you get the measurements. It moves out. Finally, the things are calibrated. But again, I'm just saying you, things might look very easy. Things might look very, very easy, but it's not as easy as it is. It has to be done. The confidence in the INS should be 200%. Then only you should understand, because a small error in the INS can induce and get the whole array into an error. It becomes totally a spoiled array. So that we have to redo the exercise again, and it will become a problem. So carry out the things in a proper way, where definitely OEM documents are very much available, but you can also have your own kind of an array, provided the INS as well as the references are very strong. So this is what we call it relatively SLAM calibrated array, similar to conventional talking with each other, get slammed. And absolute array is something very different here. In this case, in the conventional LBL array thing, we have taken a long line. We have just taken the long horizontal distance, but distance where we just measured and carry out for the rotation. But here, what we should do is, we shall take only a single thing. We just spin around the same similar kind of a thing from a distance, which is a prescribed distance and little bit higher from the surface, because there should be a good line of sight between the transponder and the transceiver. So that between that, so that they could see and carry out a spin test, so that the offsets as well as the orientation can be measured. And that's where these systems also can be done. There is also a way of carrying out references like getting two solid reference LBL transponders talking with that INS thing and carrying out an absolute calibration. That's also possible. So you just there's a methodology to carry out on a 2D. Like I said, 2D and 3D are different. There should be a consideration in 3D. You have to consider the depth and the height, whereas in 2D is just the position. So absolutely everywhere when you consider when you're going to carry out any kind of operation, so these things are to be considered to the core. We cannot leave anything out and everything there. I can talk about a lot of terminologies here. Like I have not talked about too much about the DPM model, where you know the seabed is never smooth or never flat. Seabed is totally undulated, and the respective geodesy and the error calculations and the covariances. A lot of things are there when you consider the measurements. That is where you just definitely have to spend time and understanding. These are the key fundamentals to consider and have a good thought process. So just coming back here, we could see that the calculation is very quick, and definitely you can also support me that the carbon emission is also less because we have taken everything with the Subsea itself. But there is also one more thing which I would like to add is the absolute calibration can be done only even from a vessel. That also is possible, similar to the conventional. But here the advantages of the Sparse is deploying as ROV and spin around the transponder is what seems to be kind of efficient and a quick solution so that we can extend this particular array from one, or we can even expand, or we can add up one more transponders in the seabed, and with the help of the slam calibration, we can slam them and carry out the operation. It's been that easy. So you don't need a crane or you don't need a vessel to come and push it. It's all been done. Or there are ways where you have the expanded array being done with the boxen. That preference is also we can add it. So it is kind of a flexible. If there's no definite way of carrying out the 2D and 3D calibrations, still a lot of process. Even we have spent 2 years, we have got nearly many methods to carry out the calibration, but we're just only highlighting the one most used in the industry. The biggest advantages of this one is when you carry out the vehicle positioning, you're just going to run only with 3 and with a powerful INS Kalman filter model, and you are going to carry out the operation wherever it is going to carry out. And you should also see the latest slide I'll show you the ranges. It's not going to be like this, it's going to be far. It's just going to be at least more than 1 kilometer. So it can able to talk the line of sight, and also a perfect geometry where you could talk with the transponders and get your localization powerful. If you find some INS issues there, definitely you can go somewhere in between 2 transponders and get your position updated, carry out a small error calculations and come back and carry out your operation. That also is possible. So the thing is, it is accuracy redundancy is less. So that's what the thing. You just need only 3. So once that is something we have done, but the most important thing is how actually we just take the measurements. So this is actually kind of important slide. Definitely most of you knows about it, but I just want to be clear. So when 2 transponders talk with each other, they get a slant range. They just get a range measurement. It's just you consider as range measurement. But what is important is you might not know one transponder might be slightly high and the other transponder might be slightly less. So that's one of the things we should keep in mind, that how much it is, because nowadays the transponders has got more sensors inside. It just got an accelerometer, it just got sound velocity, it has got so many things. You can just add up more sensors on board. And when you just have there's a chance that you can definitely say. But when you're going to consider 3D, you should know the depth. So how the depth is from the top of the transponder to the sea level, sea surface, similar to this. But you can see there's always a difference between these 2 depths. And when you're taking the range measurements, these things have to be considered. And this is how it's been done. And these things, when we had a training, all these things we told us every time, so that becomes a habit for us that we have to remember this whenever you put it down. So before the LBL transponder goes out of deck, make sure you measure the offsets, height, and also make sure where the depth sensor on the transponder is. So make sure that also is also measured with respect to the height. Definitely OEMs have got that in the spec, I'm 200% sure. But as a practice, you just make sure you have all those measurements with you before the transponder goes off deck. And once it goes down, you measure a depth. Definitely that can give you an indication something is not right because the height is not clear. And that is where if you have a good DTM, digital time model, which can just give you a difference in height on the sea floor. So that also to be considered. So when once you measure that horizontal range, slant range, everything, the next is you should identify the time difference, the depth difference. Sorry, depth differences. So those depth differences also to be considered. So along with that, tide variation. What is a tide variation? Because sometimes you might not know it's a tide which has really taken up the depth to a certain level, and we might mistake that height is wrong. Those things also to be very much considered here. Finally, what exactly we are going to measure? TWTT is two-way travel time. And what also we should consider is the turnaround time, because we have a lot of transponders here in the relative slam or in the Sparse LBL, it's just going to run with 2 or 3, okay, 4. But in a traditional way, we just be deploying a lot, so we just have to be very careful in turnaround time. We cannot have everything same, or there are occasions where it can be same, but as long as you know it correct, that's it. That's what is important. And there's one more thing is very important. Like I said, you have everything on the screen here, which is to be taken. What is the slant range? What is the horizontal range? What is TWTT? What is the TAT? It is very much similar to a Sparse or a conventional bill. It's very simple. The only thing is, we adding up with this, we have an INS. That's it. That's what the Sparse is going to be. But the most important thing is how to calculate the range. Yes, we have the equation. This is a very standard. But in that, you will notice only one thing. What can cause you an error? Biggest error, even if you have the good range, is the speed of sound. So please carry out the sound velocity whenever it's required, at least 6 hours. I might be also wrong because there's a policy in every system saying they have to carry out 3 hours, or some companies will have a permanent sound velocity, or some companies will have a transponder with a sound velocity provision. But if you just want to have an excellent speed of sound velocity profiler, make sure you deploy them and carry out the operation. So speed of sound in what are depth measured with this, that is very much important, because that can really trouble your calculations very much wrong. So it's a standard Pythagoras equation. So you carry out the operation and you take those ranges, and what is required, you just measure it. So just slant range and then uses a Pythagoras theorem. So this is pretty much exactly what the operations is all about. So just get your slam calibration done. Run with the powerful INS. Nowadays, all the world-class ROVs or the any kind of ROVs comes with the powerful INS. So we just already have nearly 30% of the sensor required for the specs. Along with the transceiver and the thing, there are many advantages of other metrology as well as thing. But what we are pitching here is more than that. These tasks can be utilized for more other operations as well. So this is one slide. We just want to really showcase what is that error and the adjustment the slam calibration is all about. So in the initial one, we just saw the error ellipse of the position. Like we plan the transponders, we just want to plan and keep the transponders in a place where they get an angle of cut and just get the vehicle there, so that the error get reduced on the INS to build a better Kalman filter model. But here the story is different. Here we have a transponder to be calibrated. We have a transponder to be calibrated. And what exactly we have is we have an INS with that, and we have a known positions. And with that known positions, with talks with each other, fuses onto the INS, get those ranges, and then calculates his newly built up Kalman filter and makes that INS model to be more powerful, and that really slants the new and the unconstrained D transponder to be a perfect position. It just moves to a calibrated one. You could see here. So it is just kind of an out of range. Where so what happens now is just very much solid to get one or two transponders. So the moment I just ask them to start, it will just move towards the beacon and just start communicating with two. Then you can see the error ellipse just gets reduced, and finally brings it to a spot on transponder calibration done. So this looks as easy. Frankly speaking, this looks really as easy when get deployed, provided we just understands the INS. So this is pretty much about the slant calibration and the Sparse LBL. So we just go to step in with something very specifically on INS. Like definitely the acoustics part is very much known, even INS, but there is here something we just have to really consider is the Kalman filter model, because that's important for us to keep the Sparse LBL running for long term. And still, there's a lot of things from the OEMs is getting added up and to improvise this Sparse LBL for more applications to come. So when the initial measurement unit just gives a three-dimensional acceleration and a three-dimensional three-dimensional attitude information. So all these things gets onto the initial navigation, and from there it just does all the the magnetic field compensation and all those things for the error calculations. All these things mixed together, carry out the double integration. All those things will be done on the initial navigation equations. On the other side, we have the aiding sensors, because the initial measurement has got a three axis gyroscope and three axis accelerometer. So that gives that information, raw information to be done, and there should be a lot of calculations to be done on the initial navigation equation, considering the references and considering the the earth magnetic field, as well as the oscillations. Those kind of things are there. That will be done on that. But along with that, we should also consider the aiding things, which is going to help the Kalman filter to build a better model. Because a lot of things in the initial measurement unit, like bias and the drifts, which needs to be nullified only with the external aiding sensors, which needs to portray their information. So we get a feedback from the GNSS, DVL, and the ranges, depth, altitude. So all these things are fed to the ejection filter. Then Kalman takes both the equation, both information, add up, and finally produce the updated position and orientation. So this is something like it's a very standard. So it's what I'm showing is not something created by us. It's a standard INS output. So it's something that every OEMs and every company has got the one, but this is very much standard. You just take the information from the raw unit and takes the eject information from the reference aiding unit, just add to the filters, just get the Kalman filter into updated model, and just the Kalman filter rebuilds the model every second or whenever it gets changes. So that's why if you have worked with INS, sometimes it just get drift and come back to the original position and start moving there from there smoothly. So it just gets timestamp. It just takes every information. It takes the standard deviation. It takes the covariance. So many things it will just take and formulate a perfect information required to be given as a position and orientation. So this is about that. So just we shall jump into the applications like structure installation, subsea vehicle surface vessel positioning, subsea metrology, subsea asset monitoring, and pipeline installation. But again, I'm not limiting with that. We can also deploy Sparse LBL on an hydrography, multi-beam job, on a pipeline cabling. So many things. It's getting expanded. It's getting expanded in many deployments because it's going to be quicker. It's not going to take time. It's going to be quicker. And the second biggest advantage, you just going to carry out everything in the subsea itself. So illustrating this, we got an application which as a company we have been working, and that is where we went to the OEM to get trained on a Sparse. and that is what we are just opening up, is called Subsea Residential Reference System. So we understand last 2 years before that we are spending so much time and the market is heading towards remote and residential operation. And we thought there's something we should bring in to improve the redundancy and the subsea. But not only that, and also carrying out efficiency, introducing new tools for their demanding subsea remote operations, where the subsea industry is heading towards, wants to study about different hardwares in the subsea areas to just study their kind of temperatures, the flow lines, studying that how hot is that, so many things, and also subsidence. So many things are heating up, and so many things are upcoming challenges. But there's also that we just have to have a solution which is will reduce the carbon intensity. And that is where, when we found the research to be saying that Sparse is one of the best solutions, because it can be done everything in the subsea itself without any necessity on the surface. That can be done, and which is very much possible. So that is where we introduced that one. So what you are seeing now is a traditional oil field where you just have the subsea structures and everything. But what we did is deploying just the three transponders. We just want to make the big, we want to show the array, but just the array range is 2 kilometers. That is, we just saying subjectively each space array is between 1.5 kilometers in a field where we deployed it, and what we carried out is an optimized, accurate acoustic and inertial based positioning technique for a residential during remote subsea or RMR operations. So it all starts from here, where we just deployed it in the seabed. Since it is a long range and long term, that is, it can be deployed for a long time. So you can even go to sleep mode. So we just deployed the transponder seabed, and we just asked them to carry out the referencing operation for the vehicle, to carry out different tasks on the seabed. Also collect information, share it to the to the surface, or collect everything and send it across to remotely to the cloud or whatever. But the advantages we have here is, like, which is Satish, which is very much everybody will accept, is multi-vehicle capabilities. You can able to carry out multi-vehicle capabilities at the same time, not at the same time, with the intermittent spacing time. Like, these references can be used by one vessel for one operation, and the same thing for other vessel at other operation. So it can be carried out, and all these informations are passes through the surface transceiver, or the surface transceiver can be connected with the near to your platform. But along with this, now we have the reference, but we are not stopping only with that. As I said, the transponders are becoming very intelligent by adding up more fusion sensors inside, by adding up extra sensors. So it becomes like a redundant subsea asset modeling along with navigation reference for vehicles carrying out subsea operations. You could see here that there are subsea assets. There are chances that the transponders can able to measure the vibration, as well as they could able to measure a lot of the fatigue things, and were able to measure the temperatures. That's also possible to get communicated and just flagged off and send it to the surface. So it is becoming more than a reference. It's becoming more intelligent, and it's becoming kind of important information to the customers, exactly setting about their subsea assets. So it is like the restriction is not limiting only to the, like, we don't need a kind of a surface vessel. Sometimes it's also permanently residential, and also you can able to monitor from anywhere from any part of the world with a surface system required. From there it can be shooted up through satellite to anywhere. In a very broader terms, Sparse LBL is a game changer, and is definitely is going to bringing a lot of advantages. So the introduction of the Sparse LBL is introduction of the INS and the SLAM calibration, where the SLAM calibration has got 2D and 3D calibrations, and just having three transponders with a powerful INS can be enough to carry out any kind of subsea operations. And also the arrays can be expanded easily with the seabed itself, we doesn't exactly require any kind of the surface support to carry out that operation, and also expanding that solution not only as reference and also can be an asset identifier and asset study. You can able to carry out a task related to the subsea asset by monitoring the subsea assets, temperature, and all of those. We have a lot of things, and is in this becoming intelligent. I can also do calculations in the seabed. And finally, this is becoming a very value-added tool for the residential and the remote operations or remote unmanned surface vehicles. Surface vehicle also can get references with the Sparse LBL. Even dynamic positioning DP system can utilize a Sparse LBL system as their reference for long, deeper water operations. So the applications are not limited. The applications are getting expanded. Applications are becoming big, but still, we would like to just seeking the opinion as well as the survey community to the OEMs to see how we can just take it forward to spread the Sparse LBL to the future. So with this, I'd like to really thank you for everyone for today, and I shall just jump into the question session. And very happy if you have any questions, please do feel free to ask us. Now, Rose, we are very happy to be reaching you definitely with this updated presentation, and we shall be discussing more in detail. Thank you very much. Thanks a lot. Have a great day.